What if the next chapter of human history isn't written on Earth at all, but among the stars? Picture a future where our species isn't confined to a single planet, but thrives across the cosmos. Thanks to engineering feats so audacious, they blur the line between science and science fiction. We're standing at the edge of a new era, where the impossible is being redefined every day. From colossal orbital habitats that house millions to propulsion systems powerful enough to carry us to neighboring stars, the next few decades could transform humanity from an Earth-bound civilization into a truly interstellar species. And the best part, many of these projects aren't just dreams, they're already in motion, fueled by breakthroughs in technology and a growing urgency to secure our future beyond this pale blue dot. Think about the greatest challenges we face today: climate change, resource scarcity, overpopulation. Now imagine solutions so vast they operate on a planetary scale, or even a stellar one. What if the key to saving Earth isn't just fixing what's here, but expanding our horizons to places where resources are limitless and opportunities are boundless? That's the promise of these mega projects. They're not just about exploration, they're about survival, innovation, and the sheer human drive to push beyond the known. Whether it's harnessing the power of the sun with Dyson swarms or constructing space elevators that make orbital travel as routine as a flight across the ocean, these ideas are rewriting the rules of what's possible. This journey we're about to take isn't just a list of cool concepts, it's a roadmap to humanity's next giant leap. Each of these 30 projects represents a thread in the larger tapestry of our cosmic destiny, woven together by the brilliance of engineers, the courage of pioneers, and the collective will to reach for something greater. Some will succeed, some might fail spectacularly, but every single one has the potential to change everything. So buckle up. By the time we're done, you'll see the night sky not as a distant mystery, but as a frontier waiting to be claimed, and the next generation of mega engineering could be the key that unlocks it all. The International Space Station has been humanity's outpost in low Earth orbit for over 2 decades, but it's merely the prototype for what's coming next. Imagine orbital cities where thousands live and work not as astronauts, but as ordinary citizens, scientists perfecting zero-gravity manufacturing, families experiencing life unshackled from gravity, tourists gazing down at Earth through panoramic observation decks. This vision is closer than you might think. Private companies like Axiom Space are already constructing commercial modules that will attach to the ISS before eventually forming independent space stations, while NASA's Lunar Gateway project lays the foundation for a permanent presence beyond Earth's orbit. What makes these next-generation stations revolutionary isn't just their scale, it's their purpose. Unlike the ISS, which focuses primarily on research, future orbital habitats will serve as economic powerhouses. Picture factories producing ultra-pure fiber optics in microgravity, pharmaceutical labs growing perfect protein crystals for cutting-edge medicines, and construction hubs assembling massive spacecraft that could never launch from Earth's surface. The unique conditions of space allow manufacturing breakthroughs impossible under gravity's constraints, potentially creating trillion-dollar industries that justify the cost of building these megastructures. But perhaps the most transformative aspect will be accessibility. As launch costs continue plummeting thanks to reusable rockets, orbital living could transition from exclusive government programs to something resembling today's cruise ship industry, with ticket prices dropping from millions to thousands within our lifetimes. Companies like Orbital Assembly are already designing rotating space hotels with artificial gravity, while others plan research campuses where universities and corporations can rent lab space by the month. This shift from government led to commercially driven space habitats mirrors how the internet evolved from military project to global utility and could accelerate expansion at an unprecedented pace. The real game changer, these stations won't just be destinations, they'll be launch pads. A well-equipped orbital hub could service interplanetary ships far more efficiently than launching everything from Earth's surface, where escaping gravity burns enormous fuel. Future Mars missions might begin with astronauts boarding a conventional rocket to an orbital station, then transferring to a specialized interplanetary vessel waiting in space. This two-stage approach could slash costs and risks while enabling more ambitious missions. The Lunar Gateway Station planned for orbit around the Moon will test exactly this concept, serving as both science lab and pit stop for crews heading to the lunar surface and eventually Mars. What's truly exciting is how these projects build upon each other. Each new station becomes a testbed for technologies needed by the next, creating a virtuous cycle of innovation. Lessons from the ISS informed commercial station designs, which in turn will refine techniques for building larger rotating habitats. Those megastructures may eventually evolve into full-fledged space colonies, with ecosystems carefully balanced to sustain generations. We're witnessing the first steps in humanity becoming a multi-planet species, and it all starts with these orbital way stations bridging Earth to the cosmos. While orbital stations will serve as gateways to space, the Moon offers something even more revolutionary: humanity's first permanent foothold beyond Earth. After decades of robotic exploration, multiple space agencies and private companies are now racing to establish sustainable lunar bases, transforming our barren celestial neighbor into a bustling hub of science, industry, and even tourism. Unlike the International Space Station, which requires constant resupply from Earth, these lunar outposts aim for self-sufficiency by tapping into the Moon's hidden resources. The discovery of water ice trapped in permanently shadowed craters changes everything, not just for drinking and agriculture, but as a source of oxygen for breathing and hydrogen for rocket fuel. The European Space Agency's Moon Village concept represents one of the most ambitious visions, proposing an open architecture where nations and corporations collaborate to build modular habitats that gradually expand into a full-fledged settlement. Meanwhile, China's lunar base plans focus on the South Pole's strategic locations where sunlight is nearly constant on certain peaks, providing solar power year-round just kilometers away from ice-rich craters in eternal darkness. NASA Artemis program complements these efforts by developing pressurized rovers that could serve as mobile habitats, allowing crews to conduct extended expeditions across the lunar surface. What makes these bases so valuable isn't just their scientific potential, though studying the Moon's pristine geology could rewrite our understanding of the solar system's formation, but their role as proving grounds for Martian colonization. The Moon's 1/6 gravity and lack of atmosphere create the perfect intermediate challenge between Earth and Mars operations. Technologies like closed-loop life support systems, radiation shielding, and in-situ resource utilization can be tested and perfected just 3 days from home rather than months away on Mars. Lunar regolith could even be processed into construction materials using 3D printing techniques, allowing bases to expand using local resources rather than importing every brick from Earth. The economic implications are staggering. Beyond government programs, companies like iSpace and Astrobotic are developing lunar landers to deliver commercial payloads, while others explore mining rare Earth elements or harvesting helium-3 for future fusion reactors. The Moon's weak gravity makes it an ideal launch point for deep space missions. Imagine spacecraft assembled in lunar orbit from materials mined on the surface, requiring far less fuel to reach Mars or the asteroid belt than if launched from Earth. Tourism will follow too, with firms like SpaceX already booking lunar flyby missions for private citizens. Within our lifetimes, we may see the first off-Earth luxury hotels carved into lava tubes, offering guests breathtaking views of the Earth hanging motionless in the black lunar sky. What begins as isolated scientific outposts could evolve into interconnected bases forming the backbone of a lunar economy. Picture greenhouse domes growing fresh food, solar farms stretching across the regolith, and processing plants turning ice into rocket propellant. These installations won't just support astronauts, they'll employ miners, engineers, chefs, and tour guides in what could become humanity's first truly off-world professions. The Moon won't just be a destination, it will become a springboard, classroom, and factory for our interplanetary future. Every technology perfected there, every lesson learned, brings Mars within closer reach while transforming the lunar surface from a silent wasteland into the busiest frontier in human history. Mars represents more than just our nearest planetary neighbor. It's humanity's most plausible shot at becoming a multi-planet species. While the Moon offers proximity, Mars provides something far more enticing, an environment with a 24-hour day-night cycle, polar ice caps holding vast water reserves, and geological evidence suggesting it once had rivers and lakes. These aren't just scientific curiosities, they're the building blocks for a self-sustaining civilization. Elon Musk's vision of a million-person city might sound like science fiction, but SpaceX's Starship, designed explicitly for Mars missions, is already undergoing test flights. This isn't just about planting flags, it's about laying foundations for a society that could one day rival Earth in scale and significance. The challenges, of course, are monumental. Mars' thin atmosphere offers little protection from cosmic radiation, and its surface is bombarded with solar particles that would be lethal without proper shielding. But solutions are emerging, some as simple as building habitats underground, using the planet's own soil as a radiation barrier, or constructing domes lined with water-filled walls that absorb harmful rays. NASA Perseverance rover is already testing MOXIE, a device that converts Mars' carbon dioxide-rich atmosphere into breathable oxygen, proving that critical resources can be harvested locally rather than shipped across space at astronomical cost. What makes Mars uniquely promising is its potential for terraforming, a long-term process that could thicken its atmosphere and raise temperatures enough for liquid water to flow again. While this might take centuries, early steps could begin within our lifetimes, like releasing greenhouse gases from polar ice to trigger a warming cycle. Imagine a future where genetically engineered plants thrive in Martian soil, gradually releasing oxygen and transforming the landscape from a rusty desert into a living world. This isn't just survival, it's planetary-scale gardening, with humanity as both architects and stewards of an entire biosphere. The economic case for Mars is equally compelling. Its lower gravity makes it an ideal hub for asteroid mining operations, where metals like platinum could be extracted and shipped back to Earth or used in orbital manufacturing. The planet's unique position in the solar system also makes it a strategic stopover for missions to the asteroid belt or beyond. Companies like Relativity Space are already developing rockets optimized for Martian conditions, betting on a future where interplanetary commerce is as routine as transatlantic flights are today. But perhaps the most profound impact will be cultural. A permanent Mars settlement would force humanity to rethink everything from governance to social structures, birthing innovations in law, education, and even art. Picture children born in domed cities who have never seen Earth's blue skies except in videos, or pioneers developing entirely new traditions under the pale pink Martian sun. This isn't just an extension of human civilization, it's the dawn of a new branch of it, one that could ultimately ensure our species' survival if catastrophe ever strikes Earth. The Red Planet isn't just a destination, it's the ultimate insurance policy for humanity's future, written in the rust-colored sands of an alien world. Rockets have carried humanity into space for decades, but what if there was a quieter, cleaner, and far more efficient way to reach orbit? The concept of a space elevator sounds like something straight out of science fiction, a slender tether stretching from Earth's surface all the way into space, with climbers gliding up and down like futuristic freight trains. Yet this radical idea is grounded in actual physics, and with advances in materials science, it might just become the backbone of our off-world infrastructure. Picture a world where reaching orbit costs no more than an airline ticket, where massive construction projects in space become feasible because we're no longer constrained by the brutal economics of rocket launches. The genius of a space elevator lies in its simplicity. A cable anchored near the equator would extend upward to a counterweight in geostationary orbit, approximately 36,000 kilometers high. Climber vehicles, powered by lasers or other energy sources, would ascend this ribbon at a fraction of the cost of traditional launches. Without the need for explosive rocket fuel or complex staging, each trip could carry payloads hundreds of times heavier than today's largest rockets. Think entire space station modules or massive solar arrays transported in a single run. The implications for large-scale projects, from orbital solar farms to interplanetary ships, are staggering. The catch: building such a structure requires materials with unimaginable strength-to-weight ratios, something far beyond steel or even titanium. That's where carbon nanotubes come in. These microscopic carbon structures, theoretically hundreds of times stronger than steel, could provide the necessary tensile strength to withstand the incredible forces acting on the cable. While we're still years away from manufacturing nanotubes at the required scale and purity, labs worldwide are making rapid progress. Japanese researchers have already demonstrated centimeter-long nanotube fibers with promising properties, and companies like Obayashi Corporation have announced plans to build a functional space elevator by 2050. But the challenges don't end with materials. A space elevator would face constant threats from space debris, micrometeoroids, and even atmospheric weather. Engineers propose solutions like self-healing materials, redundant strands, and active debris avoidance systems to mitigate these risks. Some designs even incorporate multiple elevators spaced around the equator to ensure redundancy. If one fails, others could keep the system operational. The International Space Elevator Consortium, a group of scientists and engineers dedicated to making this vision a reality, compares the project to the construction of the first transcontinental railroad, a seemingly impossible feat that ultimately transformed global commerce. What makes the concept so compelling isn't just the technological triumph, it's the paradigm shift it represents. Rockets will always have their place for deep space missions, but for routine access to orbit, a space elevator could reduce costs from thousands of dollars per kilogram to mere tens. This would democratize space in ways we can barely imagine, enabling everything from orbital manufacturing hubs to space tourism on a massive scale. Imagine universities sending up student-built satellites for the price of a textbook, or entire industries relocating to zero-gravity environments where they can produce materials impossible to manufacture on Earth. The ripple effects could extend far beyond economics. With cheap, reliable access to space, humanity could construct orbital solar power stations to beam clean energy back to Earth, or giant telescopes unfurled from elevator-delivered components to peer deeper into the cosmos than ever before. Asteroid mining, currently prohibitively expensive due to launch costs, could become viable overnight. And for future Mars colonists, a space elevator could serve as the ultimate loading dock, assembling massive interplanetary ships in orbit piece by piece, free from Earth's gravity well. While the timeline remains uncertain, the potential is too great to ignore. As with many mega engineering projects, the first space elevator may begin modestly, perhaps as a lunar version, where weaker gravity and no atmosphere make construction easier. A moon-based elevator could serve as a proving ground, delivering mined resources to lunar orbit for processing or transport to Earth. Success there could pave the way for the far more ambitious Earth version. One thing is clear: if humanity ever manages to weave this celestial thread between ground and sky, it won't just change how we reach space, it will redefine what's possible once we're there. Asteroids, those ancient rocky remnants from the solar system's formation, might look like lifeless chunks of debris, but they're actually floating treasure chests packed with resources that could kickstart an entirely new economic era. Imagine mining operations not on Earth, but on celestial bodies drifting between planets, where a single metallic asteroid could contain more platinum than has ever been mined in human history. Companies like Planetary Resources and Deep Space Industries are already developing the technology to turn this vision into reality, with robotic prospectors scanning near-Earth asteroids for valuable metals like gold, iridium, and rare earth elements critical for electronics and green energy technologies. But the real game changer isn't just the metals, it's the water. Locked within certain asteroids as ice, water is the oil of space exploration. When split into hydrogen and oxygen through electrolysis, it becomes rocket fuel. This means asteroids could serve as cosmic gas stations, allowing spacecraft to refuel en route to Mars or beyond without hauling all their propellant from Earth's gravity well. The implications are staggering. Missions that once seemed impossibly expensive could become routine, opening the solar system like the Transcontinental Railroad opened the American West. NASA OSIRIS-REx mission, which successfully retrieved samples from asteroid Bennu, proved we can extract material from these space rocks. Now private ventures aim to scale that up from grams to tons. The economics could reshape entire industries back on Earth. Asteroid mining might initially focus on supplying space infrastructure, but eventually it could flood markets with precious metals currently scarce on our planet. A single platinum-rich asteroid could meet global demand for centuries, potentially crashing prices, but also making everything from medical devices to renewable energy components far more affordable. Critics argue this could destabilize terrestrial mining economies, but proponents counter that it would free Earth from environmentally destructive extraction practices while providing the raw materials needed for a high-tech, sustainable future. Technological hurdles remain, of course. Mining in microgravity requires entirely new approaches. Robotic arms can't simply dig like they would on Earth. So concepts range from capturing entire asteroids in massive bags to using concentrated sunlight to vaporize and extract metals. Then there's the challenge of transporting mined materials back to where they're needed, whether that's Earth orbit, the Moon, or Mars. Some proposals suggest processing ore right on the asteroid to ship only purified metals, while others envision slinging water-rich asteroids into stable orbits near future space stations. What makes this more than just a billionaire's fantasy is the convergence of advancing technologies. Cheap, reliable robotics from terrestrial mining operations are being adapted for space, while AI-powered prospecting tools can analyze asteroid compositions from afar. Meanwhile, reusable rockets from SpaceX and others dramatically lower the cost of sending equipment to intercept these space rocks. The first missions might resemble robotic gold rushes, small, privately funded spacecraft staking claims on the most accessible asteroids, followed by larger operations once the economics prove viable. Beyond mere profit, asteroid mining could fundamentally alter humanity's relationship with space. Instead of treating it as a distant frontier only governments can afford to explore, we'd start seeing it as an extension of our industrial ecosystem, a place where resources are gathered, processed, and put to work building everything from solar power satellites to interplanetary ships. The same technologies that let us mine asteroids could eventually help us deflect hazardous ones threatening Earth, turning a potential danger into an opportunity. This isn't just about getting rich, it's about securing the materials needed to build a civilization that spans the stars. Every ton of water mined in space is a ton that doesn't need to be launched from Earth at astronomical cost. Every metal extracted from an asteroid means less environmental damage on our home planet. The asteroids that once brought extinction to dinosaurs might one day provide the resources that save humanity, fueling our expansion into the cosmos while preserving the world we leave behind. Every star in the sky represents an almost unimaginable power source. Our own sun radiates more energy in 1 second than humanity has used in its entire history. The concept of a Dyson sphere, first proposed by physicist Freeman Dyson in the 1960s, dares to ask, what if we could harness all that energy? Picture an artificial structure completely surrounding a star, capturing every photon of light to power a civilization so advanced it makes today's technology look primitive. While building such a perfect sphere remains firmly in the realm of theory, scaled-down versions called Dyson swarms could become humanity's first steps toward stellar-scale engineering within the next few centuries. These wouldn't be solid shells that would require more material than exists in our entire solar system, but vast constellations of orbiting solar collectors, each positioned to catch sunlight without blocking others. Imagine millions of mirror-like satellites working in concert, beaming energy to central stations or directly to where it's needed across the solar system. Early versions might start modestly, with a few dozen collectors supplying power to lunar bases or orbital factories, but the potential scale is breathtaking. A mature Dyson swarm could provide millions of times Earth's current energy needs, enabling projects like terraforming Mars, powering interstellar probes, or running planet-sized supercomputers. The technological leap required is staggering, but not impossible. Self-replicating robots could mine asteroids and moons for construction materials, autonomously building more collectors in an exponential growth pattern. Advances in thin-film solar cells could make these structures incredibly lightweight, while breakthroughs in wireless power transmission, already demonstrated in small-scale experiments, would allow energy to be sent wherever it's needed across vast distances. Some scientists speculate that partial Dyson swarms might emerge naturally as space-based solar power becomes economical, with each new satellite adding to an ever-growing network that gradually approaches the full vision. What makes this more than just an energy solution is how it could transform civilization itself. With such abundant power, we could synthesize food from raw elements, recycle all waste perfectly, or even control Earth's climate by redirecting sunlight. Space habitats could flourish in unprecedented numbers, each with energy budgets dwarfing entire nations today. The very structure of society might change when energy scarcity becomes a forgotten concept. No more fossil fuels, no more land-intensive wind farms, just clean, limitless power harvested from the sky. Interestingly, Dyson swarms might solve another cosmic mystery, the search for alien intelligence. Astronomers scanning distant stars for signs of advanced civilizations look for unusual infrared signatures, precisely the waste heat a Dyson structure would emit. That we haven't found any yet suggests either that such projects are impossibly difficult or that we're among the first civilizations reaching for this level of mastery over nature. Either possibility should give us pause and motivation. The road from today's solar panels to a full Dyson swarm is long, but every orbiting power station we build, every improvement in robotic construction, brings us closer to making this stellar dream a reality. In time, our descendants may look back at burning coal and splitting atoms the way we view stone tools' primitive first steps toward a future where humanity doesn't just live under a star's light, but holds its power in our hands. Imagine a city that never touches land, a self-contained world drifting through the void between stars, carrying generations of families toward a distant planet that won't be reached for centuries. This isn't a metaphor for human struggle. It's the startlingly concrete concept of generation ships, colossal arcs designed to sustain entire communities across interstellar distances. Unlike the sleek starships of science fiction that zip between planets in years, these vessels would move at more modest speeds, their passengers accepting that they'd live and die aboard the ship long before their descendants ever set foot on a new world. The engineering challenges are mind-bending, but the payoff could be nothing less than the preservation of humanity's genetic and cultural diversity across the galaxy. The heart of any generation ship isn't its engines, it's the closed-loop ecosystem that must perfectly balance oxygen, water, and food production for centuries without resupply. Picture vast hydroponic farms lit by artificial suns, where every drop of water is recycled from humidity exhaled by plants and crew alike. Waste becomes fertilizer, carbon dioxide becomes plant food, and every organism aboard plays a critical role in maintaining equilibrium. Experiments like Biosphere 2 demonstrated how fragile these systems can be when oxygen levels unexpectedly dropped. The crew struggled with symptoms resembling altitude sickness. Future ships would need redundancies upon redundancies, with backup algae tanks and microbial cultures ready to stabilize the environment at the first sign of imbalance. Artificial gravity isn't just a comfort, it's a biological necessity. Without it, children born in microgravity could develop brittle bones and weak muscles, rendering them unable to function if they ever reached a planet. Rotating sections or linear acceleration could simulate gravity, but the engineering scales are staggering. A rotating habitat module might need to be hundreds of meters across to avoid nausea-inducing Coriolis effects, while constant acceleration would require fuel reserves beyond anything chemical rockets could provide. This is where advanced propulsion like nuclear pulse drives or fusion engines becomes essential, offering the sustained thrust needed to make multi-generational voyages feasible without condemning crews to weightlessness. The social architecture of these ships may prove even more complex than their physical design. How do you maintain cultural continuity across centuries when each generation only knows life inside metal walls? Shipboard societies would need stable governance systems resilient enough to outlast Earth's nations, yet flexible enough to adapt to unforeseen challenges. Education would take on new urgency. Every child would need to master not just their specialty, but enough cross-disciplinary knowledge to keep the ship functioning if experts in critical systems were lost. Some designs propose storing frozen embryos to expand genetic diversity upon arrival, while others imagine ships carrying thousands to preserve enough cultural memory of Earth to seed a new civilization. What makes this more than a thought experiment is how many pieces are already falling into place. The International Space Station has tested life support systems for decades, while Mars habitat simulations study group dynamics in isolation. Private initiatives like the Breakthrough Starshot project are pushing propulsion technologies that could eventually scale up for crewed vessels, and astronomers discover new potentially habitable exoplanets yearly, targets for voyages that might begin as speculative blueprints in our era, but culminate in landings witnessed by descendants we'll never meet. The ultimate test won't be technological but philosophical. Are we willing to plant trees whose shade we'll never sit under? Generation ships represent humanity's longest-term thinking, a bridge between eras so distant they're barely recognizable as the same species. Yet in their careful balance of ecology, engineering, and social design, they offer something profound: proof that our vision can extend beyond individual lifespans, that we're capable of planning not just for next quarter's earnings or next election's polls, but for the survival of human culture across cosmic time. When the first of these arcs finally departs, it won't just carry passengers, it will carry the audacious belief that our responsibility to the future stretches far beyond the horizon of our own lives. The rockets we use today are like trying to cross an ocean in a rowboat, functional, but painfully slow when you consider the vast distances between worlds. Nuclear fusion could be the equivalent of inventing the steam engine for space travel, offering speeds that would make the solar system feel suddenly within reach. Unlike conventional chemical rockets that burn fuel in short, explosive bursts, fusion propulsion would provide smooth, continuous acceleration, potentially cutting the journey to Mars from months to mere weeks. The secret lies in the staggering energy density of fusion reactions. A single gram of fusion fuel can release as much energy as 8 tons of coal, making it the most potent power source known to physics. At the heart of this revolution are projects like ITER, the International Fusion Reactor under construction in France. While designed primarily to prove fusion's viability for clean energy on Earth, the same principles could be adapted for spacecraft. Picture an engine that heats hydrogen plasma to temperatures hotter than the sun's core, then directs the resulting superheated exhaust through magnetic nozzles to generate thrust. Unlike today's rockets that carry all their reaction mass as heavy fuel, advanced fusion designs might scoop hydrogen from interstellar space using vast electromagnetic nets, effectively refueling as they go, enabling voyages lasting decades without running dry. The performance numbers defy belief. Where NASA chemical rockets max out around 54,000 kilometers per hour, fusion-powered ships could theoretically reach 10% of light speed, fast enough to reach Alpha Centauri in a human lifetime. Even at more conservative estimates, Mars would become a 2-week commute, while Jupiter's moons would be months away instead of years. This isn't just about speed, it's about changing how we experience spaceflight. Astronauts wouldn't need to endure the muscle-wasting effects of prolonged weightlessness when constant acceleration could provide artificial gravity. Cargo missions could deliver construction materials to orbit in bulk, making massive projects like rotating space stations or orbital solar farms suddenly practical. Technical hurdles remain daunting. Containing fusion reactions requires either incredibly strong magnetic fields or precision-controlled laser pulses, technologies that currently fill buildings but would need to fit inside a spacecraft. Then there's the challenge of converting that raw power into thrust efficiently. Concepts like the direct fusion drive aim to solve this by channeling plasma directly into exhaust without intermediate electricity generation, potentially offering both propulsion and onboard power from a single compact reactor. Private ventures like Princeton Fusion Systems are already testing scaled-down prototypes, suggesting the gap between theory and practice may be closing faster than expected. What makes fusion particularly compelling is its safety compared to alternatives like nuclear fission. A fusion reactor can't melt down, the reaction stops instantly if containment fails. There's no long-lived radioactive waste, just harmless helium as a byproduct. This makes fusion ideal not just for crewed missions, but for planetary protection, Imagine the public outcry if a fission-powered rocket exploded during launch, scattering uranium across Florida. Fusion eliminates that risk while offering far greater performance. The ripple effects would transform space exploration. Suddenly, sending humans to mine asteroids becomes economically viable when round trips take weeks instead of years. Scientific probes could tour the outer solar system in a single mission, visiting multiple moons of Jupiter and Saturn in the time it currently takes to reach one. And crucially, interstellar travel shifts from fantasy to foreseeable future. While we may not build warp drives in our lifetime, fusion could give us the next best thing: ships that carry human explorers to other stars at speeds our ancestors would have considered miraculous. We're already seeing the first steps. NASA's investment in fusion research through projects like the Compact Fusion Reactor demonstrates serious institutional interest, while startups like Helion Energy and TA Technologies are achieving milestones in plasma confinement that edge us closer to breakthroughs. The timeline remains uncertain. Fusion has been 30 years away for decades, but the pieces are falling into place. When it finally clicks, the impact will be greater than the transition from sail to steam, from horse to automobile. The solar system will shrink before our eyes, and humanity's horizon will expand in ways we're only beginning to imagine. Turning Mars from a frozen desert into a lush, habitable world might sound like the plot of a science fiction novel, but the science behind terraforming is surprisingly concrete. The process would begin by triggering a runaway greenhouse effect, intentionally warming the planet until its frozen carbon dioxide and water vapor are released into the atmosphere. This could be done using giant orbital mirrors to focus sunlight on the polar ice caps, or factories pumping out super-potent greenhouse gases like perfluorocarbons to trap heat. Over decades, these changes would thicken the atmosphere, raising surface temperatures above freezing and allowing liquid water to flow once again. The next phase would introduce life. Lichens and cyanobacteria, some of Earth's hardiest organisms, could be seeded across the Martian surface, surviving in harsh conditions while slowly converting carbon dioxide into oxygen through photosynthesis. Genetically engineered plants might follow, designed to thrive in thin air and high radiation, their roots breaking down toxic perchlorates in the soil. Over centuries, these pioneers could transform the rusty landscape, creating pockets of breathable air and fertile ground. Lakes might reappear in ancient river valleys, fed by meltwater from the receding ice caps, while algae blooms could turn stagnant ponds into thriving ecosystems. Ethical debates rage over whether we even should reshape another world. Some argue Mars has intrinsic value in its pristine state, a frozen museum of planetary evolution. Others worry about contaminating it with Earth microbes before we've fully searched for native Martian life. But proponents counter that terraforming wouldn't erase Mars' history. It would create a new chapter where life, for the first time in billions of years, flourishes on its surface. The planet's vast canyons and towering volcanoes would remain, now framed by forests and rivers rather than endless dust. The most compelling argument for terraforming may be necessity. With Earth facing climate change and potential catastrophes, having a second habitable planet could be civilization's ultimate insurance policy. Unlike lunar bases or space stations, a terraformed Mars wouldn't require constant resupply. It could sustain itself indefinitely. Future generations might look back on these early efforts the way we view the first transatlantic cables: arduous, expensive projects that ultimately connected humanity across once impassable divides. While full terraforming would take millennia, early stages could make parts of Mars livable much sooner. Pressurized domes with breathable atmospheres might dot the landscape within a century, growing into interconnected biospheres as conditions improve outside. The first children born under those domes could live to see the day when stepping onto the Martian surface no longer requires a spacesuit, just an oxygen mask, then eventually nothing at all. What begins as a scientific endeavor could become the greatest act of planetary stewardship in history, proving that life isn't just something that happens to worlds, it's something we can nurture even among the stars. Orbiting high above the clouds where the sun never sets, vast solar arrays could solve one of Earth's most persistent energy dilemmas: intermittency. Unlike ground-based solar farms that sit idle through nights and cloudy days, space-based systems bask in unfiltered sunlight around the clock, beaming power back to Earth as steady microwaves or lasers. Japan's space agency made headlines when it successfully transmitted solar power over 500 meters wirelessly, while China aims to launch a full-scale orbital test by 2030. The implications are staggering. A single square kilometer of space-based solar panels could generate up to 2 gigawatts, enough to power over 1 million homes without consuming a single patch of Earth's surface. The secret lies in the physics of space itself. Beyond our atmosphere, sunlight is 30% more intense, with no air to scatter or absorb its energy. Solar panels in orbit don't just work continuously, they're exponentially more efficient. Engineers envision arrays spanning kilometers, their butterfly wing structures unfolding in zero gravity to capture gigawatts of power. The real breakthrough comes in transmission high-frequency microwaves directed at ground stations with pinpoint accuracy, where rectifying antennas convert them back into electricity. Safety concerns are addressed through frequency choices. The beams are tuned to pass harmlessly through clouds, birds, and even aircraft, while delivering energy with land use efficiency 10 times greater than conventional solar farms. Critics highlight the logistical hurdles. Launching thousands of tons of material into orbit remains prohibitively expensive, though reusable rockets are rapidly changing that equation. Maintenance poses another challenge. Repairing panels in geostationary orbit demands advanced robotics or astronaut crews, yet the payoff could redefine global energy politics. Countries currently dependent on fossil fuel imports could gain energy independence overnight, while disaster zones could receive instant power grids beamed from overhead. The environmental impact would be transformative, replacing smokestacks and oil derricks with silent orbital mirrors that leave no carbon footprint beyond their construction. What makes this more than just a clean energy solution is its potential to unlock other space industries. The same infrastructure that beams power to Earth could energize lunar bases, asteroid mining operations, or even future Mars colonies. Orbital factories running on this abundant electricity could manufacture materials impossible to create under gravity's pull, from flawless semiconductor crystals to ultra-strong metallic foams. Some designs even incorporate modular element solar satellites that dock like Lego bricks, allowing the network to expand as demand grows. The timeline for viable deployment hinges on two parallel advancements: cheaper space access and more efficient wireless transmission. Private ventures like SpaceX's Starship promise to slash launch costs below $200 per kilogram, while breakthroughs in phased array antennas could soon make energy transfer 90% efficient. Early systems might start small, powering remote islands or supplementing national grids during peak demand. But the ultimate vision is a constellation of solar stations supplying baseline power for entire continents, their unflickering beams stitching together a global web of clean energy. This isn't just about keeping lights on, it's about reimagining civilization's energy backbone. With orbital solar, hurricanes wouldn't knock out power grids for weeks, and developing nations could leapfrog past coal plants straight to space-based solutions. The technology carries echoes of Nikola Tesla's dream of wireless power, but instead of towering coils on the ground, the transmitters float silently in space, harnessing the pure, endless light of the sun to power the world below. When historians look back on this century, the moment we learn to harvest stars may shine as brightly as when we first tamed fire. Picture a laboratory where flames burn as perfect spheres, metals mix without containers, and crystals grow without defects. This isn't some futuristic fantasy, but the everyday reality of manufacturing in space. The absence of gravity transforms basic physical processes, allowing materials to form in ways impossible under Earth's constant downward pull. Companies like Varda Space Industries are already launching miniature factories into orbit, where they produce exotic fiber optics and life-saving pharmaceuticals before returning the products to Earth. These aren't just experiments, they're the first stirrings of an industrial revolution that could relocate entire supply chains to the final frontier. The magic lies in what microgravity eliminates: convection currents that distort crystal growth, sedimentation that causes impurities, and container interactions that introduce defects. On Earth, producing flawless protein crystals for cutting-edge cancer drugs often requires countless failed attempts, but in orbit, these molecules assemble into perfect lattices as if following an invisible blueprint. The International Space Station has already demonstrated this with experiments growing monoclonal antibodies, key components in drugs that treat everything from arthritis to COVID, with purities unmatched by terrestrial labs. Similar breakthroughs are happening with Zeblan glass, an ultra-transparent material that could make fiber optic cables 10 times more efficient if produced without the microscopic imperfections gravity inevitably creates. What makes this more than just a scientific curiosity is the economic potential. A single kilogram of certain space-manufactured drugs can be worth millions, easily justifying the cost of orbital production. Varda's compact factories fit inside standard satellite buses, operating autonomously for months before returning capsules packed with valuable cargo. Other ventures focus on producing artificial retinas in orbit, delicate structures requiring perfect layering of organic tissues, or ultra-strong alloys where metals with different densities mix evenly for the first time. These aren't niche products, they're materials that could redefine entire industries, from telecommunications to organ transplants. The ripple effects extend far beyond high-value specialty items. Imagine construction beams made from space-forged metallic foam, lighter than aluminum but stronger than steel, revolutionizing everything from skyscrapers to electric vehicles. Or solar panels with orbit-grown perovskite crystals converting sunlight at unprecedented efficiencies. Even everyday products like semiconductors could leap forward. Microgravity allows chip components to self-assemble into three-dimensional structures impossible to etch lithographically, potentially extending Moore's law for decades. The common thread: processes we've struggled to perfect on Earth become elegant and straightforward when gravity steps out of the equation. Critics highlight valid challenges, from the high costs of orbital launches to the difficulties of remote quality control. But the economics are shifting rapidly. Just as the internet evolved from military project to global utility, space manufacturing is transitioning from government-run experiments to commercially viable operations. Reusable rockets have already slashed launch costs tenfold since 2010, while advances in robotics and AI enable autonomous factories needing minimal human oversight. The business models are equally innovative. Some companies plan subscription-based access to orbital facilities, while others focus on turnkey production services where customers never need to leave Earth's atmosphere. This industrial migration could follow a familiar arc: first luxury goods, then critical technologies, finally commoditized products as infrastructure scales. The 18th century had spice trade routes, the 20th had oil tankers, and the 21st may have regular cargo runs returning space-forged wonders from orbital factories. What begins as a trickle of high-value pharmaceuticals and exotic materials could blossom into an off-world industrial base supporting lunar mines and Mars colonies. The factories of tomorrow may not stand on any planet's surface, but float gracefully between worlds, their silent crucibles turning raw stardust into the building blocks of our interstellar future. Living in space comes with an invisible tax on the human body. Without gravity's constant pull, muscles wither, bones lose density, and even the heart weakens from lack of resistance. The International Space Station has shown us that even rigorous daily exercise can't fully counteract these effects, leaving astronauts struggling to walk after just 6 months in orbit. But what if we could bring gravity with us? The solution might lie in one of the oldest tricks in spaceflight's playbook, rotation. By spinning a habitat like a merry-go-round, centrifugal force can press inhabitants outward, mimicking gravity's pull in a phenomenon even Einstein found fascinating. The mathematics behind this are surprisingly straightforward. A station rotating just 4 times per minute with a radius of 50 meters could simulate Earth's gravity along its outer rim, enough to keep bones strong and organs functioning normally. Science fiction nailed this concept decades ago with iconic designs like 2001, A Space Odyssey's spinning wheel, but today's engineers are translating that vision into blueprints. Companies like Orbital Assembly are developing the first commercial stations with rotating sections, where scientists could work under artificial gravity by day and retreat to stationary hubs for sleep, eliminating the disorientation some feel in constant spin. Even partial gravity, say, Mars 38% might suffice to mitigate health risks while reducing the structural demands of rapid rotation. The real innovation lies in how these designs scale. Early stations might feature compact centrifuges for exercise pods, where astronauts spend hours daily to counteract muscle loss. Next-gen habitats could employ dual counter-rotating rings to cancel out gyroscopic effects that would otherwise make docking spacecraft a nightmare. The most ambitious concepts envision Stanford Torus-style megastructures cities in space with kilometer-wide rotating bands where trees grow tall and children play in parks under synthetic skies. NASA Gateway Station will test a critical midpoint, a small centrifugal module attached to its lunar orbit outpost, providing data on how partial gravity affects biology over extended periods. But engineering challenges abound. Building large rotating structures requires materials strong enough to withstand immense tension without tearing apart, while precise balancing becomes crucial. An uneven mass distribution could send the entire station wobbling like an unbalanced washing machine. Solutions range from active compensation systems using movable counterweights to segmented designs that flex slightly under stress. Then there's the human factor. Some people experience motion sickness in rotating environments, though studies suggest most adapt within days. The payoff, however, could redefine space colonization. Imagine Martian settlers spending their transit under Earth like gravity, arriving fit and ready instead of weakened by months of weightlessness. What makes artificial gravity more than just a health measure is its psychological impact. Floating endlessly can feel liberating at first, but long-term residents of the ISS describe missing simple pleasures: pouring coffee, feeling their weight on a mattress, even the act of walking. Rotating habitats restore these tactile anchors, making space feel less alien. Future stations might offer tiered gravity levels: lunar gravity for light industry where delicate equipment operates best, Martian gravity for social zones, and full Earth gravity in medical bays where bone regeneration is critical. This flexibility could prove vital for interplanetary species adapting to multiple worlds. The ultimate test will come when we attempt sustained reproduction in space. Animal studies show disturbing trends. Mice born in microgravity often fail to develop normal balance systems. Artificial gravity could provide the stable environment needed for embryos to develop properly, ensuring humanity's expansion into the cosmos isn't limited by biology. As these stations evolve from experiment to necessity, they'll do more than solve a problem. They'll transform space from a place we endure to one where we truly belong, with bodies as healthy as our ambitions. Imagine sending a message across millions of kilometers of space with absolute certainty that no one could intercept or decode it, not even with unlimited computing power. This isn't science fiction, it's the promise of quantum communication, a technology that could revolutionize how we transmit data across the solar system. At its core lies a bizarre but brilliant property of quantum mechanics, the ability to encode information in particles of light so delicate that any attempt to eavesdrop would instantly alter their state, revealing the intrusion. China's MISHA satellite proved this principle works even in orbit, successfully establishing the first space-to-ground quantum key distribution link in 2017. That breakthrough opened the door to what could become the most secure communications network in history, one spanning planets, immune to the cyber threats that plague Earth's internet. The magic happens through quantum entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, changing one instantly affects its partner, no matter how far apart they are. This allows for the creation of encryption keys that are fundamentally unhackable, unlike traditional methods, based on complex math problems that future quantum computers might crack. Picture a future Mars colony receiving daily data packets from Earth, each secured by keys generated from pairs of entangled photons. Even if hostile actors had access to the transmission lines, the laws of physics themselves would foil their efforts. The implications for military, financial, and personal communications are staggering, but the real game changer is for interplanetary infrastructure. Robotic probes, asteroid miners, and crewed missions could all coordinate with Earth in perfect secrecy, sharing critical navigation data or scientific findings without fear of sabotage or interference. Building this cosmic internet won't be simple. Quantum signals are notoriously fragile, easily disrupted by atmospheric turbulence or even stray photons from distant stars. MISHAs overcame this by using ultra-sensitive detectors and precise pointing systems, but extending the technology across interplanetary distances will require new breakthroughs. One solution might involve a constellation of quantum relay satellites placed at strategic points like gravitational sweet spots called Lagrange points, where they could receive and retransmit quantum signals with minimal degradation. Another approach could use quantum repeaters devices that don't measure the fragile quantum states but amplify and redirect them, preserving their secrecy across vast stretches of space. The timeline for a fully functional quantum network depends on parallel advancements in satellite miniaturization and error correction. Current quantum communication systems are bulky and power-hungry, but labs worldwide are racing to develop chip-scale quantum transmitters that could fit inside standard CubeSats. Error rates also remain high over long distances, though techniques like entanglement purification, essentially distilling perfect quantum links from imperfect ones, show promise. The European Quantum Communication Infrastructure Initiative aims to have a continent-wide quantum-secured network operational by 2030, while NASA Jet Propulsion Laboratory is exploring how to adapt these technologies for deep space missions. What makes this more than just a security upgrade is how it could transform space exploration itself. Future missions might deploy autonomous quantum nodes upon arrival at distant worlds, creating instant secure links back to Earth without waiting for conventional radio signals that take minutes or hours to traverse the void. Astronauts on Mars could video conference with mission control with lag no worse than a terrestrial Zoom call, thanks to quantum protocols that eliminate traditional encryption delays. And perhaps most profoundly, a solar system-wide quantum network would enable coordination between robotic swarms across asteroids, moons, and planets, all communicating through an unhackable lattice of entangled particles, turning the void between worlds into a bustling highway of information. The challenges are immense, but the stakes are higher. In an era where cyber warfare threatens everything from power grids to election systems, extending that vulnerability to space infrastructure could be catastrophic. Quantum communication offers a way out, a foundation for trust in an increasingly interconnected solar system. As we plant the seeds of interplanetary civilization, ensuring those roots can't be poisoned may be the most far-sighted investment we make. The quiet revolution happening in labs today could soon echo across the cosmos, weaving an invisible web of light that binds humanity's future outposts in perfect, unbreakable synchrony. Imagine landing on Mars to find an entire base already constructed, pressurized habitats stocked with supplies, solar arrays humming with power, and greenhouses bursting with crops, all built by an army of robots that arrived years earlier. This vision hinges on self-replicating machines, the ultimate force multipliers for space colonization. Unlike traditional robots that perform fixed tasks, these advanced systems would mine local materials, refine them into components, and assemble copies of themselves, exponentially growing their workforce without a single shipment from Earth. The concept isn't new. Mathematician John von Neumann sketched the idea in the 1940s, but today's breakthroughs in artificial intelligence and 3D printing are turning theory into tangible blueprints. The beauty of this approach lies in its efficiency. Transporting even a single kilogram to Mars costs tens of thousands of dollars with current technology, making traditional construction methods prohibitively expensive. But a single ton of carefully designed robotic seeds could theoretically multiply into thousands of tons of infrastructure given time and raw materials. Lunar regolith contains oxygen, silicon, and metals perfect for manufacturing solar panels or structural beams, while Martian soil offers iron and sulfur for machinery. These robots wouldn't just build, they'd evolve. Early prototypes might resemble today's mining drones equipped with basic 3D printers, but successive generations could incorporate specialized tools for welding, electronics assembly, or even bioengineering algae tanks for life support systems. NASA's Innovative Advanced Concepts program has funded studies on self-replicating systems, including a lunar factory that produces copies of itself using only moon dust and sunlight. Meanwhile, universities are testing robotic swarms that collaborate like termites, constructing complex structures without centralized control. The key innovation is hierarchical replication, simple robots creating more sophisticated versions over time, gradually expanding their capabilities until they can fabricate everything from radiation shielding to microchip-filled control modules. This isn't just about brute force construction, it's about encoding the principles of biology into machines, allowing them to adapt and specialize based on environmental demands. Critics raise valid concerns about runaway replication, the nightmare scenario of a grey goo scenario where machines consume entire planets. Safeguards would be hardwired into their design, strict limits on reproduction cycles, dependency on rare earth-supplied catalysts for critical components, or even embedded biological triggers that degrade machinery after set time periods. The goal isn't unchecked multiplication, but controlled bootstrapping, creating just enough infrastructure to support human arrival while leaving ecosystems intact. The implications extend far beyond our solar system. Self-replicating probes could become humanity's interstellar ambassadors, traveling for centuries to neighboring stars at sublight speeds, then using local resources to build communication relays or even prepare worlds for eventual colonization. Projects like Breakthrough Starshot envision miniature probes reaching Alpha Centauri in decades, but larger replicators could follow, slowly transforming entire asteroid belts into way stations for future generations. What makes this more than an engineering challenge is its philosophical dimension. These machines would carry humanity's collective knowledge in their code, the sum of our construction techniques, material science, and survival strategies, acting as both builders and teachers for off-world civilizations. The first robot to replicate itself on Mars won't just assemble habitats, it'll lay the foundation for a new chapter in human history, one where our reach is no longer limited by the cargo capacity of rockets. When astronauts finally walk through those prefabricated airlocks, they'll be stepping into a future built not by human hands, but by our ingenuity distilled into machines that turn alien landscapes into homes. The discovery of thousands of exoplanets has transformed astronomy from a search for distant points of light into a hunt for future homes. While Mars and the Moon dominate near-term colonization plans, these alien worlds orbiting other stars offer something far more profound: the possibility of Earth-like environments where humanity could thrive without artificial habitats or terraforming. The closest known exoplanet, Proxima Centauri b, orbits within its star's habitable zone just 4 light-years away, with a surface temperature that might allow liquid water. But reaching these distant shores demands technologies that make today's interplanetary missions look like rowboats crossing a pond. Breakthrough Starshot embodies the audacity required for such a leap. This initiative plans to launch gram-scale probes propelled by ground-based lasers, accelerating them to 20% of light speed, fast enough to reach Alpha Centauri in just 20 years. These tiny spacecraft, equipped with cameras and sensors thinner than a human hair, would beam back images of alien coastlines and atmospheric data, helping identify which worlds merit more ambitious follow-up missions. While Starshot focuses on reconnaissance, its underlying photonic propulsion technology could eventually scale to crewed vessels, using massive light sails kilometers across to catch laser beams for gradual acceleration across interstellar distances. The challenges of settling exoplanets dwarf even those of Martian colonization. At interstellar distances, communication delays stretch from minutes to years, requiring settlements to operate with near-total autonomy. Genetic diversity becomes critical: a founding population large enough to avoid inbreeding over generations, yet small enough to transport practically. Closed-loop ecosystems would need flawless reliability, recycling every molecule of water and breath of air for centuries without resupply. Some proposals suggest sending frozen embryos or DNA printers to overcome the biological bottleneck, while others envision generation ships where entire communities live and die during the millennia-long voyage. What makes these distant worlds worth the inconceivable effort is their potential to be more than just backups for Earth. They could be upgrades. Picture a planet with slightly stronger gravity that prevents bone loss, or a thicker atmosphere that blocks cosmic rays without ozone depletion. Some exoplanets orbit red dwarfs, stars so stable they could shine for trillions of years, offering civilizations durations unimaginable on Earth. Others might harbor novel resources or biological precursors that revolutionize medicine or materials science. The very act of adapting to these environments could spur evolutionary leaps, with human descendants diverging into new forms optimized for alien conditions. The timeline for such settlements remains speculative, but the first steps are already underway. Next-generation telescopes like the Habitable Worlds Observatory will analyze exoplanet atmospheres for biosignatures, oxygen, methane, or other gases hinting at life. Meanwhile, advances in hibernation research and AI-driven ecosystem management could solve the challenges of long-duration voyages. While our generation may never see humans walk on an exoplanet, the data we gather today will guide those who do, turning what seems like science fiction into an eventual reality. The stars have never felt closer or more full of possibility. The silent void of space might seem like the least hospitable place to grow a salad, but breakthroughs in orbital agriculture could soon turn spacecraft and distant colonies into self-sufficient breadbaskets. Traditional farming relies on soil, sunlight, and seasons. Three things in short supply off-world, but hydroponic and aeroponic systems flip the script, delivering nutrients directly to plant roots through mist or water solutions. NASA's veggie experiment aboard the International Space Station has already yielded crisp red romaine lettuce, zinnias, and even radishes, proving that crops can thrive in microgravity when given the right care. These aren't just science fair projects, they're the foundational research for feeding crews on 3-year Mars missions or sustaining lunar bases where resupply shipments might arrive only annually. What makes these systems revolutionary isn't just their ability to function without soil, it's their precision. LED arrays tuned to specific wavelengths can accelerate plant growth while using a fraction of the energy of traditional farming, with red and blue light optimized for photosynthesis while minimizing wasted heat. Advanced sensors monitor pH levels and nutrient concentrations in real time, automatically adjusting the mix to prevent deficiencies. The result: crops that grow faster and healthier than their Earth-bound counterparts, with some experiments showing 30% higher yields in controlled orbital environments. Companies like Interstellar Lab are scaling this concept, designing modular biopods for lunar and Martian use that can cultivate everything from strawberries to soybeans under pressurized domes. Genetic engineering will play an equally critical role. Scientists are tailoring plants to survive harsh off-world conditions, varieties with shorter roots for compact hydroponic systems, or leaves that transpire less to conserve precious water. Some researchers are even experimenting with crops that produce higher oxygen output or edible biomass more efficiently, like dwarf wheat strains that yield full-sized grain heads on compact stalks. The European Space Agency's ME-LISSA project takes this further, developing closed-loop systems where plants recycle astronaut waste into food, oxygen, and clean water, a self-sustaining micro-ecosystem where nothing goes to waste. The psychological benefits might outweigh the nutritional ones. Imagine a Mars colonist's morale boost from biting into a fresh tomato after months of reconstituted meals, or tending a fragrant basil plant as a reminder of Earth. Studies on the ISS show that caring for plants reduces stress and improves cognitive function critical for crews isolated in the deep space equivalent of a submarine. Future stations might feature entire greenhouse modules as communal spaces, where residents gather under the soft glow of grow lights surrounded by vertical gardens of kale and snap peas. Scaling up presents fascinating challenges. Low gravity means water doesn't drain normally, requiring clever engineering to prevent roots from drowning. Pollination in microgravity, essential for fruiting plants like tomatoes, might depend on robotic bees or gentle air currents. And while leafy greens grow well now, calorie-dense staples like potatoes and peanuts will need larger systems. The solutions are as innovative as the problems. 3D printed root scaffolds to guide growth, ultrasonic misters that deliver nutrients without clogging, and AI systems that predict crop needs before humans notice issues. The ultimate goal goes beyond survival rations. Orbital farms could become gourmet hubs, cultivating specialty crops like saffron or vanilla that are prohibitively expensive to launch from Earth. Lunar vineyards might one day produce wine aged in low-gravity cellars, while Martian greenhouses grow coffee beans under artificial sunlight. This isn't just about avoiding starvation, it's about bringing the flavors, rituals, and comforts of home across the cosmic frontier. When the first child born on Mars asks what Earth's forests smelled like, the answer might come from a cluster of genetically preserved oak saplings thriving under a dome, their leaves whispering in carefully circulated air, a living bridge between worlds. Space may seem infinite, but the precious orbits around Earth are becoming dangerously crowded, a celestial junkyard of defunct satellites, spent rocket stages, and millions of razor-sharp fragments whipping around the planet at 17,000 miles per hour. A single screw lost during a spacewalk in 1986 still orbits today, packing the kinetic energy of a bowling ball thrown at highway speeds. This isn't just clutter, it's an escalating threat that could trap humanity on Earth if left unchecked, as cascading collisions render key orbits unusable. The Kessler syndrome, a nightmare scenario where each impact creates more debris, triggering further collisions, could cut off access to space for generations. But a new wave of orbital janitors is rising to meet the challenge, turning sci-fi cleanup concepts into real-world missions. Astroscale's ELSA-D mission proved the core technology works: a satellite that can locate, approach, and safely capture a derelict spacecraft using magnetic docking plates. Their next-generation craft will target actual debris, maneuvering carefully to avoid unintended collisions before dragging objects down to burn up in the atmosphere. Meanwhile, Europe's Clear Space One takes a different approach, deploying robotic tentacles to grapple large debris like a cosmic octopus handling delicate cargo. The real innovation lies in their autonomous guidance systems, which calculate optimal approach vectors while accounting for the chaotic tumble of debris, some spinning wildly, others drifting unpredictably after decades in orbit. The scale of the problem demands equally bold solutions. Remove Debris, a European project, tested a harpoon and net system to snare larger objects, proving even medieval hunting techniques have a place in 21st century space operations. Other proposals include ground-based lasers that nudge debris into decaying orbits using photon pressure, or gossamer thin aerogel sails that increase atmospheric drag to accelerate re-entry. The most ambitious vision comes from Japan's JAXA, developing an electrodynamic tether that would slow debris by interacting with Earth's magnetic field, a celestial fishing line that reels in trash without physical contact. What makes this more than an environmental campaign is the economic imperative. Every telecom satellite lost to debris costs hundreds of millions, while the International Space Station regularly performs avoidance maneuvers that disrupt research. Insurance premiums for launches are skyrocketing as the risk of collision grows, threatening the viability of everything from GPS networks to climate monitoring systems. Startups like Leo Labs are building radar networks to track objects as small as 2 centimeters, providing the traffic control system space desperately needs, while regulatory bodies push for mandatory end-of-life disposal plans requiring satellites to deorbit themselves or move to graveyard orbits when their missions end. The ultimate solution may lie in prevention rather than cleanup. Next-generation satellites like OneWeb's constellation incorporate built-in deorbit systems, while SpaceX's Starlink satellites autonomously avoid collisions using ion thrusters. Some companies are exploring biodegradable satellites that vaporize upon re-entry, leaving no harmful residues, but for the existing mess, only active removal will suffice. a task requiring international cooperation rivaling the Paris Climate Accords in complexity. When the first commercial debris removal service docks with a defunct weather satellite to give it a controlled funeral in the atmosphere, it won't just be taking out the trash, it'll be preserving humanity's pathway to the stars for generations to come. The concept of hypersleep, once confined to the realm of science fiction, is inching toward reality as scientists crack the code of metabolic suspension. Imagine astronauts embarking on a years-long journey to Mars, not in cramped quarters counting down every meal, but in a state resembling deep hibernation, their heart rates slowed to a crawl and body temperatures lowered just enough to dramatically reduce the need for food, water, and oxygen. This isn't just about comfort, it's a game changer for interplanetary logistics. A crew in torpor might require only 5% of the usual consumables, turning what would be a cargo-heavy mission into something lean and efficient. Research into this field draws inspiration from nature. Brown bears and Arctic ground squirrels routinely enter states of hibernation, slowing their metabolisms by up to 95% while preserving muscle and bone mass, a biological cheat code that could hold the key to human space travel. Scientists at SpaceX and NASA have partnered with medical researchers to explore hydrogen sulfide therapy, a method that safely induces a hibernation-like state in mammals by mimicking the body's response to extreme cold. Early trials with rodents have shown promise, with subjects revived after weeks of suspended animation with no apparent cognitive or physical deficits. The next step, adapting these techniques for primates and eventually humans. The engineering challenges are as fascinating as the biology. Hypersleep chambers would need to maintain perfect equilibrium, monitoring vitals, administering precise drug cocktails, and adjusting temperature down to a fraction of a degree. Some designs resemble high-tech cocoons with embedded sensors and automated systems to prevent blood clots or muscle atrophy during extended stasis. Others propose immersing astronauts in specialized fluids that support circulation and prevent pressure sores during months of immobility. The European Space Agency's studies even suggest combining torpor with artificial gravity through slow rotation, creating a hybrid system where crews cycle between suspended animation and active periods to maintain health. Beyond Mars, this technology could unlock the stars. Generation ships' vast arcs carrying thousands on centuries-long voyages suddenly become plausible if most passengers spend the journey in hypersleep, awakening only for maintenance shifts or emergencies. The psychological benefits are equally compelling. A crew skipping monotonous years of transit would arrive mentally fresh, avoiding the cabin fever that plagues long-duration missions. There's poetic symmetry to humanity may conquer the final frontier by borrowing strategies from the humblest creatures, proving once again that the future of spaceflight is written in the language of life itself. Ethical questions linger, of course. How do we ensure perfect reliability for systems tasked with sustaining life unattended for years? What protocols govern waking someone mid-journey in an emergency? Yet the potential outweighs the uncertainties. When the first astronauts drift into hypersleep en route to the Red Planet, it won't just be a technical milestone, it'll be the moment we transcend one of space travel's most fundamental constraints, the frailty of the human body against the vastness of time and distance. Solar sails turn the faintest whisper of starlight into a revolutionary propulsion system, no fuel required. Just the gentle but relentless push of photons bouncing off vast, mirror-thin membranes. The concept sounds deceptively simple. Sunlight exerts physical pressure, and over time, that minuscule force can accelerate a spacecraft to incredible speeds without burning a single drop of rocket propellant. The Planetary Society's Light Sail 2 proved this wasn't just theory in 2019, successfully raising its orbit around Earth using nothing but sunlight, a milestone that echoes the moment humans first harnessed wind to cross oceans. But this isn't just about replicating ancient sailing in space. It's about unlocking a fundamentally new way to explore the cosmos, where journeys to distant stars become feasible not by carrying enormous fuel loads, but by riding the cosmic wind. The magic lies in the scalability. Unlike chemical rockets that obey the tyranny of the rocket equation, where every gram of fuel requires more fuel just to lift itself, solar sails grow more effective the larger and lighter they're built. Imagine a probe the size of a shoebox unfurling a sail thinner than a human hair but spanning a kilometer, its reflective surface catching sunlight like a parachute in a hurricane. Over weeks and months, that constant push adds up, enabling speeds that could reach 10% of light speed with laser assistance fast enough to reach Alpha Centauri in a human lifetime. Breakthrough Starshot's vision takes this further, proposing a ground-based laser array that could blast a fleet of micro sails to 20% light speed, turning interstellar exploration from a multi-generational dream into something achievable within decades. Materials science breakthroughs are turning these visions into reality. Traditional solar sails relied on aluminum-coated mylar, but next-generation designs use atomically thin materials like graphene or metallic foams that weigh almost nothing while withstanding the brutal temperature swings of space. Some prototypes even incorporate smart materials that can change reflectivity on command, allowing ships to tack against the solar wind like a yacht maneuvering against the breeze. The real game changer, though, is the marriage of solar sails with miniaturized electronics, tiny probes packed with sensors, cameras, and AI that can explore entire star systems without the need for heavy propulsion systems or power-hungry engines. But the challenges are as vast as the sails themselves. Navigation becomes a delicate ballet of angles and trajectories, requiring constant adjustments to catch the optimal photon breeze. Dust particles in interstellar space, though tiny, could puncture sails at high velocities, necessitating self-healing materials or redundant layers. Then there's the problem of slowing down without fuel to burn. Sail-based probes might streak past their targets at breathtaking speeds, gathering only fleeting glimpses. Clever solutions are emerging, like using the destination star's own light pressure as a brake or deploying secondary sails as cosmic airbags. What makes solar sails more than just a niche technology is their democratizing potential. Traditional deep space missions cost billions, but a solar sail-powered probe could be built by a university lab for less than the price of a sports car. Imagine dozens of these sails fanning out across the solar system, studying asteroids, monitoring solar weather, or even acting as communication relays for distant colonies, all without the constraints of fuel budgets or launch windows. The Japanese Ikaro's mission proved sails could work beyond Earth orbit, cruising past Venus in 2010, while NASA's upcoming solar cruiser aims to use a sail the size of a tennis court to study the sun's poles. The ultimate promise lies beyond our solar system. A fleet of laser-boosted sails could serve as humanity's eyes and ears among the stars, beaming back images of exoplanet coastlines or anomalous cosmic phenomena. Some designs even envision sails carrying tiny labs capable of analyzing interstellar chemistry or sampling the magnetic fields between stars. This isn't just about exploration, it's about presence, a way for our civilization to reach beyond the cosmic neighborhood without waiting for warp drives or generation ships. When the first sail-powered probe catches sunlight in another star system, it won't just be a technological triumph, it'll be proof that humanity has learned to ride the very waves of the universe itself. Space tourism is shifting from a billionaire's fantasy to a tangible bucket list experience, with companies like Blue Origin and Virgin Galactic already sending civilians on brief but breathtaking suborbital hops. These 11-minute adventures offer more than just bragging rights. They provide a visceral, life-altering perspective. Passengers describe seeing Earth's curvature against the blackness of space, feeling weightlessness for the first time, and returning with a newfound appreciation for our planet's fragility. While critics dismiss these jaunts as frivolous, their psychological impact mirrors the overview effect experienced by astronauts, a cognitive shift in awareness that often sparks environmental activism and global cooperation among those who have seen our world from above. But suborbital flights are just the appetizer. Orbital Assembly's Pioneer Station, slated for completion by 2030, represents the next leap, a rotating luxury hotel where guests spend days, not minutes, in space. Designed with artificial gravity to minimize discomfort, its panoramic suites and zero-gravity bars could make orbital vacations as routine as Caribbean cruises. The economics are equally disruptive. As reusable rockets drive launch costs down, analysts' project prices could drop from millions to tens of thousands per ticket within 2 decades, putting space within reach of upper-middle-class travelers. Imagine honeymooners toasting over Earthrise views, or retirees attending orbital cooking classes where floating globules of sauce become gourmet art. The ripple effects extend far beyond tourism. These ventures are pioneering technologies that will democratize space access, like safety systems refined through thousands of civilian flights, or compact life support architectures adaptable for lunar outposts. Even the hospitality angle matters. Learning to design comfortable, aesthetically pleasing habitats in orbit directly informs future Mars bases, and the cultural impact could be profound. When thousands return from space annually, not just a handful of astronauts every few years, public support for space exploration may surge, creating a virtuous cycle where tourism revenue funds scientific expansion. Yet challenges loom. Regulatory frameworks remain patchwork, with nations scrambling to establish liability laws for commercial spaceflight accidents. Health screenings must balance accessibility with safety should someone with mild hypertension be barred from a flight, and sustainability questions persist. While modern rockets are cleaner than early models, scaling tourism to thousands of launches yearly demands greener propulsion. Companies are already addressing these hurdles, from Virgin Galactic's hybrid rocket engines that slash emissions to Axiom Space's astronaut training programs for civilians. The ultimate vision, a future where children save allowance money for orbital birthday trips and space stewardess becomes a mainstream career. When Orbital Assembly's first hotel spins up its gravity wheel, it won't just mark a new industry, it'll signal that the cosmos is no longer the domain of governments and elites, but the next frontier of human experience, open to anyone daring enough to book a ticket. Right now, sending an email to Mars would be like mailing a letter by carrier pigeon, possible, but painfully slow and prone to getting lost along the way. The average delay for a signal between Earth and the red planet ranges from 5 to 20 minutes each way, making real-time communication impossible and turning simple data transfers into day-long affairs. But what if astronauts on Mars could video chat with mission control as easily as we call overseas, or download terabytes of scientific data in seconds? That's the promise of an interplanetary internet, a celestial web of relay satellites, laser links, and revolutionary protocols designed to knit our scattered outposts into a seamless network. NASA Delay/Disruption Tolerant Networking, or DTN, is the first step toward this cosmic connectivity. Unlike Earth's internet, which assumes constant connections, DTN treats space's unpredictable delays and blackouts as features, not bugs. Imagine it as a galactic postal service. If a Mars orbiter can't immediately forward data to Earth because planets have rotated out of alignment, it holds the information like a patient courier, waiting for the next available transfer window. This store and forward approach has already proven itself aboard the International Space Station, where it routinely routes scientific data through a labyrinth of shifting satellite connections. The European Space Agency took this further in 2012, using DTN to control a robotic rover in Germany from a simulated Mars orbiter, demonstrating how future astronauts might remotely operate drones on the Martian surface despite the lag. The real magic begins when these protocols merge with next-generation hardware. Picture a constellation of relay satellites parked at gravitational sweet spots called Lagrange points, their laser crosslinks forming a backbone stretching from lunar orbit to the asteroid belt. Lasers packing data into beams 1,000 times denser than radio waves could enable broadband speed transfers across millions of kilometers. A laser communications relay demonstration recently shattered records, beaming 1.2 gigabits per second from geostationary orbit to Earth, fast enough to download a high-definition movie in under a minute from 22,000 miles away. Applied interplanetarily, this tech could let a Mars colony stream ultra-high resolution scans of newly discovered caves, or transmit real-time medical imaging during surgeries guided by Earth specialists. But the challenges are as vast as the distances involved. Solar conjunctions, periods when the sun blocks the line of sight between planets, could black out communications for weeks, requiring autonomous systems to keep critical operations running. Radiation storms might scramble signals mid-transmission, demanding error correction algorithms far more robust than those protecting your Netflix stream. And then there's the security nightmare. A hacked interplanetary router could spoof commands to distant spacecraft or eavesdrop on sensitive transmissions, necessitating quantum-level encryption to safeguard the network. What makes this more than just a technical achievement is how it could redefine exploration itself. With reliable high-bandwidth links, scientists across planets could collaborate in virtual labs, analyzing Martian soil samples together as if peering into the same microscope. Families separated by light minutes might share holographic birthday parties, their avatars laughing together in real time despite being worlds apart. And when the first interstellar probes reach Alpha Centauri, this network could become their tether home, a chain of laser relays stretching between the stars, ensuring that even at 4 light-years away, humanity's farthest footsteps remain connected to the pulse of Earth. The interplanetary internet won't just transmit data, it'll carry culture, emergency alerts, and the collective knowledge of our species across the void, turning isolated outposts into nodes of a single, sprawling civilization. When archaeologists someday uncover the first Martian server farm, they may recognize it not just as a technological artifact, but as the foundation stone of something unprecedented, a society that thinks across planets as easily as we once did across continents. Mars' thin atmosphere isn't just a scientific curiosity, it's the primary barrier standing between the red planet and human habitability. Solar wind, that relentless stream of charged particles from the sun, has been stripping away Martian air for billions of years, leaving behind a wispy shell just 1% as dense as Earth's. But what if we could flip the script, using cutting-edge technology to shield Mars from this cosmic erosion, and even help it regain a breathable sky? The answer might lie in an audacious plan to park giant electromagnets at strategic points in space, creating an artificial magnetic field that could deflect solar wind like an invisible umbrella. The concept builds on a phenomenon we already exploit closer to home: Earth's natural magnetic field. which acts as a planetary force field diverting harmful radiation. NASA proposed Mars' L1 Lagrange point shield would mimic this effect by placing a powerful dipole magnet at a gravitational sweet spot between Mars and the Sun. Here, the magnet's influence would extend far enough to cradle the planet in a protective bubble, reducing atmospheric loss to near zero levels. Over centuries, natural processes like volcanic outgassing and comet ice deposits could then thicken the atmosphere without constant solar wind interference. Early simulations suggest this approach might restore Mars to half of Earth's atmospheric pressure within just a few millennia, a blink in geological time. What makes this strategy so compelling is its elegance compared to brute force terraforming. Instead of manufacturing an entire atmosphere from scratch, a process requiring unimaginable amounts of energy and resources, we'd simply give Mars the tools to rebuild itself. The planet already holds vast reserves of frozen carbon dioxide at its poles and water ice beneath its surface. Shielded from solar wind, these reservoirs could sublimate naturally, creating a greenhouse effect that warms the planet and releases even more gases in a self-reinforcing cycle. Some models indicate temperature increases of up to 4 degrees Celsius within decades of shield activation, enough to begin melting ice caps and jump-starting planetary-scale climate change. The engineering challenges are as breathtaking as the vision itself. A functional magnetic shield would require superconducting coils kilometers across, maintained at cryogenic temperatures in the vacuum of space. Power could come from compact nuclear reactors or vast solar arrays, but the real innovation lies in the shield's positioning. Unlike static planetary magnets, this artificial field would need active stabilization to compensate for Martian seasons and solar storms. Researchers are exploring plasma-based solutions, clouds of charged particles tethered to the main magnet that could extend and reshape the protective bubble like cosmic origami. Critics argue the timeline renders the project impractical, but incremental benefits could appear much sooner. Even partial atmospheric thickening would reduce radiation exposure for surface colonists, making habitats safer and solar panels more efficient. Increased air pressure would also lower the risk of explosive decompression accidents while improving the performance of Martian aircraft. Perhaps most intriguingly, a denser atmosphere might permit liquid water to exist temporarily in low-lying regions, creating fleeting habitats for extremophile microbes, either native Martian life or Earth organisms introduced intentionally to jumpstart ecosystems. The philosophical implications run deep. By erecting a magnetic shield, we wouldn't just be altering a planet, we'd be assuming the role of planetary stewards on an unprecedented scale. This technology could become the ultimate test case for responsible terraforming, demonstrating whether humanity can repair worlds as well as we've damaged them. Future generations might look back on the deployment of Mars' magnetic shield as the moment we graduated from inhabitants of a single planet to caretakers of multiple worlds, wielding physics as gently as a gardener wields a trowel. While the full vision may take centuries, early prototypes could emerge surprisingly soon. Miniature versions might first protect lunar bases from radiation, or even be adapted to deflect dangerous solar flares threatening Earth satellites. Each step forward would teach us more about manipulating planetary environments, knowledge that could prove vital if we ever need to repair Earth's own magnetic field during a future pole reversal. The red planet's thin atmosphere has long been seen as an implacable obstacle to colonization, but with the right technology, it might just become the proving ground for humanity's greatest act of planetary healing. Particle accelerators on Earth have revolutionized physics, smashing atoms together to uncover the building blocks of matter, but they're fundamentally limited by the planet they're anchored to. Vibrations from seismic activity, temperature fluctuations, even footsteps in distant corridors introduce microscopic errors in alignment. The atmosphere absorbs or distorts certain particles before detectors can analyze them. Now imagine these behemoth instruments freed from Earth's constraints, floating in the pristine silence of space where the only vibrations come from the hum of their own machinery. Space-based particle accelerators could crack open cosmic mysteries that have eluded scientists for generations, from the true nature of dark matter to the existence of extra dimensions. The advantages of orbit are staggering. Without atmospheric interference, detectors could capture ultra-high-energy cosmic rays particles traveling at nearly light speed that arrive from distant galaxies in their purest form. These cosmic messengers carry clues about black holes and supernova, but Earth's atmosphere shatters them into secondary particles like a prism splitting light. A space-based accelerator could catch them intact, reading their signatures like cosmic barcodes. Similarly, experiments searching for dark matter, the invisible substance making up 85% of the universe's mass, would gain unprecedented sensitivity. On Earth, background noise from radioactive decay in rocks or even the walls of underground labs masks potential dark matter signals. In orbit, surrounded by nothing but vacuum, detectors could listen for the faintest whisper of these elusive particles. Designing these orbital behemoths requires radical rethinking. Traditional accelerators like CERN 27-kilometer Large Hadron Collider rely on massive superconducting magnets to steer particles, impossible to launch intact. Instead, space accelerators might use compact plasma Wakefield technology, where lasers create waves in ionized gas that surf particles to high energies in mere meters rather than kilometers. The International Linear Collider Collaboration has already prototyped these systems, achieving accelerations 1,000 times stronger than conventional methods. In microgravity, these plasma channels could maintain perfect alignment for days, enabling collisions with precision down to atomic scales. The real prize lies in energy scales unreachable on Earth. Orbital accelerators could tap into the solar system's natural magnetic fields as cosmic boosters, slinging particles along interplanetary paths to velocities that would require a terrestrial accelerator larger than the Moon. Picture an experiment where protons launched from near Mercury, whipped by solar wind and planetary magnetism, collide near Mars with energies mimicking the first trillionths of a second after the Big Bang. Such events might create particles predicted by string theory or reveal hidden symmetries in the laws of physics. The data would stream back to Earth via laser link, each packet a potential revolution in our understanding of reality. Challenges abound, from powering these instruments likely requiring orbiting solar arrays or compact nuclear reactors, to shielding delicate electronics from solar flares. Yet the pieces are falling into place. The alpha magnetic spectrometer on the ISS has demonstrated long-term particle detection in space, while private ventures like Volt Energy aim to deploy small-scale plasma accelerators in orbit by 2030. Even asteroid mining could play a role. Metallic asteroids rich in iron and nickel could provide raw materials for constructing accelerator segments in situ, avoiding the cost of launching everything from Earth. What makes this more than just a tool for physicists is its potential to spark unforeseen technologies. The same plasma acceleration methods could propel spacecraft to relativistic speeds, while ultra-precise collision data might inform new quantum computing architectures. When the first orbital accelerator beams its findings home, we won't just be peering deeper into the universe's secrets, we'll be writing the next chapter of human ingenuity, one particle collision at a time. A lunar space elevator might sound like the stuff of Arthur C. Clark novels, but the physics behind this concept is surprisingly straightforward, and the engineering is inching closer to reality every year. Unlike an Earth-based elevator that would need to withstand our planet's crushing gravity and atmosphere, a moon elevator could be built with existing materials. The moon's weaker gravitational pull and lack of atmospheric interference make it the perfect testing ground for this revolutionary transport system. Picture a ribbon-like tether stretching from the lunar surface to a counterweight in space, with robotic climbers shuttling payloads up and down like cosmic freight trains. This single structure could slash the cost of moving materials from the moon's surface to orbit by a staggering 90%, turning lunar mining operations from science fiction into industrial reality. The genius of this design lies in its simplicity. Anchored near the moon's equator, possibly at the rim of a crater for stability, the tether would extend roughly 50,000 kilometers toward Earth, terminating at a captured asteroid or manufactured counterweight balanced at the Lagrange point where lunar and Earth gravity cancel each other out. Solar-powered climbers would ascend this ribbon at a leisurely pace, carrying raw materials mined from the moon's regolith or prefabricated components for orbital construction projects. Without the need for rocket fuel or complex launch systems, each trip would cost mere dollars per kilogram compared to the thousands required by traditional lunar landers. Companies like Liftport Group have already conducted Earth-based tests of tether materials and climber prototypes, proving the core technology isn't just theoretical. What makes this more than just a lunar conveyor belt is how it could transform the entire economics of space exploration. The moon holds vast resources of oxygen, silicon, and metals locked in its soil, materials that could be processed into rocket fuel, solar panels, or even structural components for spacecraft. A space elevator would allow these resources to be shipped to orbital depots where they could supply missions headed to Mars or beyond. Instead of launching every kilogram of fuel and supplies from Earth's deep gravity well, future expeditions could top off their tanks at a lunar orbit fuel station stocked by the elevator. NASA Artemis program has already identified this concept as a potential game changer, with studies suggesting a lunar elevator could pay for itself within a decade through reduced launch costs alone. The engineering hurdles, while significant, are surmountable with current technology. The tether material, likely a carbon nanotube composite, would need to be strong enough to handle the tension between lunar gravity and the centrifugal force at the counterweight. Fortunately, the moon's weaker pull means the required tensile strength is within reach of materials we can produce today, unlike an Earth elevator which would require fibers 100 times stronger. Power transmission poses another challenge, with proposals ranging from laser beams fired from the lunar surface to superconducting lines running the length of the tether. Japan's Obayashi Corporation, which aims to build an Earth space elevator by 2050, has already developed working prototypes of wireless power transfer systems that could be adapted for lunar use. Perhaps the most exciting aspect is how this infrastructure could evolve. An initial lunar elevator might start modestly, a single tether handling a few tons per month. But as demand grows, additional elevators could form a network around the moon's equator, creating what scientists call a lunar space pier. These multiple anchor points would allow simultaneous launches and landings, with cargo transferred between tethers via orbital hubs. Some visionaries imagine these hubs growing into full-fledged shipyards, where lunar aluminum and titanium are fashioned into spacecraft components without ever being hauled down to Earth. The moon could become the industrial heart of our solar system economy, with its elevators serving as the conveyor belts feeding orbital factories. The ripple effects would extend far beyond logistics. Permanent lunar bases would become exponentially more viable with regular, affordable cargo runs bringing supplies and returning scientific samples. Tourism might follow imagined luxury hotels at the base of elevator terminals, where visitors could watch Earthrise from the moon's surface before taking a climber up to orbiting cruise ships. Most importantly, mastering this technology on the moon would provide invaluable data for constructing an eventual Earth-based elevator, proving the concept works on a smaller scale before attempting the 1,000 times more difficult terrestrial version. When historians look back on humanity's expansion into space, they may mark the construction of the first lunar space elevator as the moment we stopped merely visiting other worlds and began truly inhabiting them. More than a transportation system, it would be an umbilical cord connecting two branches of human civilization, one on Earth, one on the moon, with materials and ideas flowing freely between them. The elevator's ribbon, glinting in the sunlight as it stretches toward the stars, would stand as both an engineering marvel and a symbol of our species' determination to reach beyond the cradle of our birth. Venus isn't just Earth's closest planetary neighbor. It's a scorching hellscape with surface temperatures hot enough to melt lead and crushing atmospheric pressures equivalent to being a kilometer underwater. Yet 50 kilometers above this inferno lies one of the most surprising potential habitats in the solar system, a temperate band of atmosphere where the pressure and temperature mirror Earth so closely that a human could step outside wearing just an oxygen mask and light thermal protection. This sweet spot is the target of NASA's Havoc mission concept, high-altitude Venus operational concept, a daring proposal to float research cities in the Venusian skies like a fleet of futuristic hot air balloons. These wouldn't be the rigid airships of the 1930s, but ultramodern habitats filled with breathable air that naturally floats at Venus's mid-atmosphere level. Picture massive, helium-filled envelopes supporting multi-level research stations, their solar-powered propellers adjusting position to maintain altitude while scientists study the planet below through drone probes. The physics is elegantly simple. Earth's air is lighter than Venus's carbon dioxide-rich atmosphere at that altitude, meaning a habitat filled with our familiar nitrogen-oxygen mix would float like a cork in water. Unlike Mars missions requiring complex pressure suits for every excursion, Venusian researchers might work on open-air balconies wearing little more than weatherproof jackets, a surreal experience of tending gardens or repairing equipment while suspended above acid clouds. The scientific payoff could rewrite planetary science textbooks. Venus's runaway greenhouse effect makes it a cautionary tale for Earth's climate future, but we've barely scratched its mysteries. Floating labs could analyze sulfuric acid cloud chemistry in real time, track mysterious ultraviolet absorbers swirling in the atmosphere, and decode the planet's bizarre super-rotation where winds whip around the globe faster than the planet itself spins. Some theories even suggest microbial life might persist in Venus's temperate cloud layers, an electrifying possibility given the recent detection of phosphine gas, a potential biosignature. Havoc drones could sample these clouds directly, hunting for extremophiles that redefined where we think life can exist. Surviving this environment demands ingenious engineering. The stations would need coatings resistant to sulfuric acid corrosion, along with systems to extract water from trace atmospheric vapor. Power could come from advanced solar cells optimized for Venus's perpetual overcast, or even wind turbines tapping into the planet's hurricane-force upper winds. Most critically, the habitats would require fail-safes to prevent catastrophic sinking, perhaps backup balloons or emergency buoyancy tanks to maintain altitude if primary systems faltered. NASA prototypes suggest clusters of modular habitats linked by flexible walkways, creating a floating campus that could expand as missions grow from weeks to months and eventually to permanent settlements. The long-term vision transforms these research outposts into something grander, self-sustaining cloud cities harvesting resources from the atmosphere itself. Carbon dioxide could be split into oxygen for breathing and carbon for manufacturing, while sulfuric acid might be processed into fertilizer for hydroponic farms. Over decades, these floating colonies could evolve into way stations for deep space missions, leveraging Venus's gravity well for efficient slingshot maneuvers to the outer solar system. Some architects even sketch designs for recreational spaces, zero-gravity sports arenas suspended between habitats, or observation decks where residents watch Venus's perpetual sunset through the swirling clouds. What makes this more than just a technical exercise is how it reframes our relationship with hostile worlds. Instead of battling Venus's extremes at the surface, we'd adapt to its most habitable niche, just as life on Earth occupies everything from ocean trenches to mountaintops. Future generations might gaze down at Venus's glowing lava plains from their aerial verandas, not as conquerors of an impossible environment, but as inhabitants who found the one place in that hellscape where humanity could thrive. The lesson echoes across our interstellar ambitions. Sometimes survival isn't about changing a world, but finding the pocket where we fit into its rhythms. Black holes, those cosmic vacuum cleaners of infinite density, might seem like the last place you'd look for a power source, but their very nature makes them potential energy gold mines. The Penrose process, proposed by physicist Roger Penrose in 1969, reveals how an advanced civilization could theoretically extract energy from a rotating black hole's ergosphere, the warped region of space-time just outside the event horizon where nothing can stand still. Here's how it would work. Objects entering this zone get dragged around by the black hole's spin like leaves caught in a whirlpool. If a craft were to split in two at precisely the right moment, one half could plunge into the abyss while the other escapes with more energy than it arrived with, effectively stealing a portion of the black hole's rotational momentum. The math checks out under perfect conditions. Up to 20% of a black hole's mass energy could be harvested this way. The engineering required boggles the mind. First, you'd need to locate a suitably spinning black hole, likely a stellar mass-care black hole left behind by a collapsed star. Then comes the delicate ballet of positioning your energy collector, a swarm of autonomous probes or a megastructure orbiting at the edge of the ergosphere, where space-time itself twists like a wrung-out towel. These harvesters would need to withstand tidal forces that could spaghettify conventional materials, not to mention the relentless pull of gravity trying to drag them into oblivion. Some designs propose using microscopic black holes as portable power plants created artificially in particle accelerators and fed just enough matter to keep them spinning at optimal energy output levels without growing dangerous. What makes this more than a physicist's pipe dream is how it mirrors energy solutions we're already exploring. The Penrose process operates on principles similar to tidal energy harvesting on Earth, where we capture the moon's gravitational pull through ocean currents. Even solar panels share a conceptual link. Both tap into cosmic phenomena far more powerful than anything human-made. The difference is scale. A single stellar black hole could provide the energy equivalent of trillions of nuclear reactors, making it the ultimate renewable resource for civilizations looking to power Dyson swarms or interstellar travel. Critics highlight the obvious hurdles, not least being that the nearest known black hole, Gaia BH1, is 1,500 light-years away. Yet the same was once said of uranium deposits before we understood how to harness them. Breakthroughs in quantum physics might one day allow us to create micro-black holes in labs, bypassing the need to travel to these cosmic giants. Others argue that manipulating space-time to this degree would require mastery of negative energy or exotic matter materials that currently exist only in theory. But remember, the laptops we take for granted today would have seemed like magic a century ago. The deeper implication isn't just about energy, it's about intelligence. A civilization capable of harvesting black holes has likely graduated from planetary to galactic scale engineering, using the fabric of reality itself as a tool. They might not even need physical infrastructure. Some theories suggest advanced beings could encode information directly into black hole mergers, turning colliding singularities into cosmic telegraphs. Whether humanity ever reaches this stage remains unknown, but the mere possibility reshapes how we think about life's potential in the universe. The cosmos may be full of species who have turned their local black holes into power outlets, quietly fueling empires we can't yet imagine. Far from being dark destroyers, black holes could become the ultimate engines of creation, their ferocious spins lighting up galaxies for civilizations bold enough to plug into the void. 66 million years ago, a mountain-sized asteroid rewrote Earth's history in a single fiery instant, wiping out the dinosaurs and resetting the evolutionary clock. Today, that same cosmic threat looms over human civilization, with an estimated 15,000 near-Earth asteroids large enough to cause regional devastation if they struck. But unlike the dinosaurs, we're not helpless against this celestial roulette. NASA's Double Asteroid Redirection Test, or DART, proved in 2022 that humanity can literally nudge an asteroid off course, slamming a refrigerator-sized spacecraft into Dimorphos at 14,000 miles per hour and altering its orbit. This successful test marks the dawn of planetary defense as an engineering discipline, transforming asteroid deflection from Hollywood fantasy into actionable science. The genius of DART kinetic impactor strategy lies in its simplicity. No nuclear explosions or complex gravity tractors, just raw momentum transfer at astronomical speeds. Think of it as a cosmic game of billiards where even a tiny push years in advance can make an asteroid miss Earth by thousands of miles. DART impact changed Dimorphos' 12-hour orbit by 32 minutes. Far exceeding predictions and proving small velocity changes compound dramatically over interplanetary distances. Future missions like ESA's HERA will study the crater in detail, refining our models for deflecting larger threats. But kinetic impactors are just the opening move in planetary defense's playbook. Next-generation systems could deploy entire fleets of interceptor satellites parked at gravitational waypoints, ready to swarm incoming threats. Picture a coordinated strike where multiple impactors hit an asteroid sequentially, first to break up monolithic rocks into smaller, more manageable fragments, then to steer those pieces onto safe trajectories. Alternative approaches include gravity tractors, spacecraft that hover near an asteroid for years, using their minuscule gravitational pull to gradually alter its path. For truly dire scenarios, nuclear standoff bursts remain an option, not to obliterate the asteroid but to vaporize a portion of its surface, creating jet-like thrust from the ejected material. Early warning is equally critical. Projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will catalog 90% of potentially hazardous asteroids above 140 meters within a decade, objects large enough to devastate continents. But the real game-changer may be space-based infrared telescopes like NEO Surveyor, scheduled for launch in 2027. Orbiting between Earth and the Sun, it'll spot heat signatures of dark, carbon-rich asteroids that optical telescopes miss. The same stealthy rocks that caught astronomers off guard when one exploded over Chelyabinsk in 2013 with 30 times the energy of Hiroshima's atomic bomb. The ultimate vision, a planetary defense network combining early detection with rapid response deflection satellites stationed at Lagrange points like a celestial neighborhood watch, backed by asteroid reconnaissance probes that analyze composition and structure upon detection. Nuclear electric propulsion could enable interceptors to reach threats within months rather than years. International cooperation is already taking shape through the UN's Space Mission Planning Advisory Group, ensuring no single nation bears the burden of protecting the entire planet. What makes this more than just disaster prevention is how it redefines our relationship with near-Earth objects. These same deflection technologies could one day enable asteroid mining by allowing precise orbital placement of resource-rich rocks. The spacecraft developed to save Earth might also help fuel its expansion into space, turning existential threats into economic opportunities. When the next dinosaur killer finally appears in our telescopes, and statistically, it's not a matter of if but when humanity won't stare helplessly at the sky. We'll have the tools to calmly nudge it aside, rewriting cosmic history not as victims, but as architects of our own destiny. Imagine controlling a Martian rover with just your thoughts, no joysticks, no voice commands, just pure neural intention translating into precise robotic movements millions of kilometers away. This isn't the plot of a sci-fi novel. It's the near-future promise of brain-computer interfaces like Neuralink adapted for space exploration. While Elon Musk's neurotechnology venture currently focuses on medical applications here on Earth, its implications for astronauts could redefine how humans interact with machines beyond our atmosphere. In the harsh, isolating environment of space, where every millisecond counts during emergencies and bulky spacesuit gloves limit dexterity, direct brain-to-machine communication might evolve from luxury to necessity. The core advantage lies in latency, or rather, the near elimination of it. Traditional controls require physical movement or vocalization, both of which create delays in critical scenarios. Picture an astronaut repairing a solar array during a solar storm. With a neural interface, their impulse to adjust a tool could become action before their hand even twitches. Neuralink's ultra-thin threads implanted in the motor cortex detect neuronal activity with unprecedented precision, potentially allowing control over robotic arms, drones, or even entire spacecraft systems through intention alone. NASA experiments with non-invasive EEG headsets on the International Space Station have already proven the concept works in microgravity, but implantable interfaces could offer resolution fine enough to manipulate individual robotic fingers or interpret complex commands like realign the communications array to Earth azimuth. Communication itself could undergo a radical transformation. Current deep space missions suffer from agonizing delays, up to 20 minutes for a signal to travel between Mars and Earth. Neural interfaces might enable a form of compressed telepathy, where astronauts transmit concepts or pre-verbal thoughts directly to colleagues or AI systems. Instead of painstakingly describing a malfunction over crackling radio channels, a crew member could share a mental schematic of the issue, complete with intuitive highlights. Early prototypes from companies like Synchron demonstrate how implanted devices can translate brain signals into text. Adapted for space, this could evolve into a hybrid language combining words, images, and raw data streams. The psychological benefits could be equally profound. Isolation and confinement during long-duration missions pose serious mental health risks, but neural interfaces might offer countermeasures. Direct brain stimulation could help regulate circadian rhythms disrupted by alien day-night cycles, or even mitigate space-induced neuroplasticity, the worrying phenomenon where prolonged microgravity physically alters brain structure. Some studies suggest targeted neurofeedback could enhance stress resilience, effectively training astronauts' brains to maintain optimal performance during crises. There's even speculative research into shared virtual experiences via brain-to-brain linking, allowing crews to mentally escape their metal habitats for brief intervals, perhaps walking through forest simulations together to combat sensory deprivation. Of course, the technology isn't without its hurdles. Implant surgery in microgravity presents uncharted medical territory. How does cerebrospinal fluid behave when suturing a neural lace? Radiation poses another challenge. Cosmic rays could theoretically induce erroneous signals in delicate implants, requiring novel shielding approaches or error-correcting algorithms. Ethically, the line between therapeutic enhancement and unnecessary augmentation blurs quickly. Should we modify astronauts' brains purely for mission efficiency? And crucially, no one yet knows how prolonged neural interface use might affect creativity or emotional depth qualities just as vital to exploration as technical skill. Yet the potential rewards justify the risks. Consider a future where paralyzed patients on Earth operate computers via Neuralink today, while their counterparts on Mars pilot terraforming bots with the same technology tomorrow. The same implants that restore mobility to injury victims could allow astronauts to feel the grip pressure of a robotic hand tending a lunar hydroponic farm, or sense the strain in a space station's structural beams through artificial proprioception. This isn't just about convenience, it's about creating a seamless symbiosis between human intuition and machine precision, where both thrive in environments neither could conquer alone. When the first neurally augmented astronaut adjusts a radio telescope with a thought or comforts a homesick crewmate through shared memory projection, it'll mark more than a technical milestone. It'll signal the dawn of a new kind of spacefarer, one whose tools aren't just in their hands, but woven into the very fabric of their consciousness, turning the void between worlds into an extension of human will rather than an impassable barrier. Moon dust isn't just a nuisance clinging to astronauts' boots, it's the ultimate building material waiting to be tapped. Imagine landing on the lunar surface with nothing but a swarm of robots and watching them transform the gray powder beneath your feet into pressurized habitats, landing pads, and radiation shields. This vision is closer than you might think, thanks to advances in space-based 3D printing that treat regolith as cosmic concrete. The European Space Agency's PAVA project has already demonstrated lasers capable of melting lunar soil into solid bricks, while NASA's a Moon-to-Mars Planetary Autonomous Construction Technology program is developing robots that could autonomously assemble these bricks into domes using nothing but sunlight and local materials. The genius of this approach lies in its simplicity. Lunar regolith contains all the essential ingredients for construction: silicon, aluminum, calcium, and iron oxides just waiting to be sintered or bound together. Some techniques use concentrated sunlight or microwaves to fuse the dust particles, creating structures as strong as gypsum concrete. Others mix regolith with polymers made from recycled astronaut waste or in situ resources to form moldable composites. The result: buildings that don't need a single brick shipped from Earth, with walls thick enough to block cosmic radiation while maintaining structural integrity in the Moon's low gravity. But habitats are just the beginning. The same technology could print roads to prevent abrasive dust from damaging rover wheels, or solar panel mounts aligned for maximum energy capture. NASA Artemis missions plan to test a microwave sintering printer called the Lunar that could fabricate emergency spare parts on demand. Imagine a broken oxygen regulator being replaced by a unit printed overnight from local materials rather than waiting months for a resupply launch. The implications for Martian colonization are even more profound. where similar soil composition could allow settlers to live off the land from day one. The challenges are as granular as the regolith itself. Moon dust is notoriously sharp and electrostatically charged, clogging machinery and sticking to every surface. Engineers are countering this with vibration systems and non-stick coatings inspired by lotus leaves. Another hurdle is scaling. Early printers might produce 1 brick per hour, but future systems could employ swarms of mobile bots working in tandem, their efforts coordinated by AI that adapts designs to real-time material properties. What makes this more than just a construction breakthrough is how it reshapes the economics of space exploration. Every kilogram of material sourced on the moon saves roughly $100,000 in launch costs. Over time, these savings could fund entire colonies, with 3D printers acting as the backbone of a self-sustaining off-world economy. Picture lunar outposts evolving from cramped metal cans to sprawling regolith domes with vaulted ceilings, their interiors lined with printed ceramic tiles made from the very ground they stand on. The ultimate test will come when the first printed structure withstands a meteoroid impact or a lunar quake, proving that humanity's future in space isn't just about bringing our technology to new worlds, it's about learning to build with what those worlds provide. When astronauts walk through an arch made of fused moon dust, they'll be stepping into more than a shelter. They'll be entering an era where the universe itself becomes our hardware store. Wormholes, those hypothetical tunnels through the fabric of spacetime, have long been the stuff of science fiction, offering the tantalizing possibility of stepping across the galaxy as easily as walking through a door. But what if this cosmic shortcut isn't just a fantasy? Recent advances in theoretical physics suggest that traversable wormholes, while still firmly in the realm of speculation, might not violate the known laws of the universe. The key lies in exotic matter, a hypothetical substance with negative energy density that could theoretically prop open a wormhole's throat long enough for something or someone to pass through. While we've yet to discover such matter, quantum experiments like the Casimir effect have demonstrated that negative energy densities can exist in microscopic amounts, teasing the potential for scaling up this phenomenon. The math behind stable wormholes is both elegant and mind-bending. Einstein's general relativity allows for their existence as solutions to certain equations, but these cosmic tunnels would require extreme conditions to remain traversable. Picture a spacetime funnel pinched at the center like an hourglass, its walls lined with exotic matter to prevent collapse. The entrance might appear as a shimmering sphere, a gateway where light bends so sharply that you'd see distorted images of the destination before even stepping through. Unlike black holes which crush everything in their grip, a properly engineered wormhole could offer a smooth passage, connecting two distant points in the universe as if they were adjacent rooms. The implications are staggering. A functioning wormhole network would render interstellar distances meaningless, allowing real-time travel between star systems without the constraints of light speed. Colonizing exoplanets would become as logistically straightforward as establishing supply routes between continents. Scientists could study the early universe by sending probes through wormholes positioned near cosmic inflation-era relics, while families might vacation on alien worlds as casually as flying across oceans today. The very concept of a frontier would dissolve when every point in the cosmos is just a step away. Of course, the challenges dwarf even the wildest engineering feats humanity has attempted. Stabilizing a wormhole would require energies comparable to manipulating entire neutron stars, and the exotic matter needed might exist only in quantities smaller than atoms. Some theories propose workarounds using quantum vacuum fluctuations or cosmic strings as theoretical scaffolding, but these ideas remain untested. There's also the unsettling possibility that wormholes could destabilize catastrophically, potentially creating time paradoxes or birthing new universes with unpredictable physics. The very act of traversing one might alter its structure, stranding travelers in an unrecognizable space-time, yet the pursuit isn't purely speculative. Laboratories like Fermilab are studying quantum entanglements, spooky action at a distance, for clues about non-local space-time connections. Advanced simulations on quantum computers are modeling microscopic wormhole dynamics, with Google's Sycamore processor recently simulating a holographic wormhole in a simplified model. These experiments don't create actual wormholes but explore whether the underlying physics could someday be engineered. Meanwhile, telescopes scour the cosmos for natural wormhole signatures, anomalies like gamma-ray circles, or gravitational lensing patterns that can't be explained by black holes alone. What makes wormholes more than just a physicist's pipe dream is their potential to solve fundamental cosmic puzzles. They could offer a unified framework linking quantum mechanics and gravity, two domains that currently resist reconciliation. Some models even suggest wormholes might explain dark energy's mysterious effects on universal expansion. The same mathematics that describes wormholes also appears in theories of quantum information, hinting that spacetime itself might emerge from deeper, entangled quantum structures. Whether humanity ever stitches together a traversable wormhole remains unknown, but the quest itself is reshaping our understanding of reality. Each theoretical breakthrough, from negative energy solutions to quantum gravity models, brings us closer to answering whether the universe permits such shortcuts. And if it does, the galaxy would cease to be a collection of distant stars and become a neighborhood, with every world a doorstep away, waiting for someone bold enough to turn the knob. These 30 awe-inspiring projects aren't just engineering feats, they're the blueprints for humanity's next evolutionary leap. From the lunar factories that could become our first off-world industries to the quantum networks that might one day connect civilizations across star systems, each represents a fundamental shift in how we interact with the cosmos. What's remarkable isn't just their scale, but how they interconnect. Asteroid mining could supply materials for orbital megastructures, while fusion propulsion systems might carry the first crews to those distant rocks. This isn't random technological progress, it's the emergence of an entirely new ecosystem of spacefaring capabilities. Consider how these ideas build upon each other like cosmic dominoes. The space elevators that slash launch costs make orbital solar farms economically viable, which in turn provide clean energy to power lunar bases, where scientists perfect the closed-loop life support systems needed for Mars colonies. Each project fills a critical niche in this grand puzzle, addressing challenges that have confined humanity to Earth for millennia. The self-replicating machines that could construct Martian habitats also solve the distance problem. They're the workforce that arrives first, preparing the way for human settlers years or even decades later. The timeline for these ventures spans generations, yet the pace is accelerating in ways that defy expectations. Technologies like 3D printing with lunar regolith or asteroid prospecting drones were pure science fiction when today's engineers were children. Now they're laboratory-tested realities with flight hardware in development. This acceleration curve suggests that projects currently deemed centuries away, like Dyson swarms or interstellar probes, might materialize within our grandchildren's lifetimes. The seeds we're planting today, from fusion research to quantum communication, are the roots of breakthroughs we can scarcely imagine. Beyond the technical triumphs lies something even more profound: the cultural transformation these projects will spark. A child born today might choose between careers as an orbital habitat architect, Mars terraforming specialist, or quantum network engineer, jobs that don't yet exist. The overview effect, that cognitive shift astronauts describe when seeing Earth from space, could become a shared human experience as space tourism democratizes access to the cosmic perspective. These mega projects won't just change where we live, they'll reshape how we think about our place in the universe. The challenges ahead are as daunting as they are exhilarating. Radiation shielding, psychological resilience during decades-long missions, the ethics of altering other worlds, these aren't engineering problems with neat solutions, but ongoing conversations that will evolve with each new discovery. Yet history shows that humanity's greatest achievements emerge from such complexity. The Apollo program wasn't just about rockets. It required breakthroughs in computing, materials science, and human physiology that rippled across society. Today's mega projects will have similar cascading effects, spinning off technologies that improve life on Earth even as they open the stars. What makes this moment unique is that for the first time, the dream of becoming an interplanetary species has moved from speculation to strategic planning. The blueprints exist, the prototypes are being tested, the international collaborations are forming. Whether it's the first Martian child taking their breath in a dome-enclosed garden or the inaugural transmission received through an interstellar quantum network, these milestones will stand beside fire, agriculture, and electricity as turning points in human history. The projects we've explored aren't just reshaping our future, they're redefining what it means to be a civilization with the vision to reach beyond its cradle and the courage to make that vision real. So which of these cosmic ambitions resonates with you? Is it the poetic symmetry of rebuilding Mars' atmosphere, the raw ingenuity of black hole energy harvesting, or the quiet revolution of orbital farms that could feed worlds? The conversation starts now in comment sections and classrooms, research labs and living rooms, wherever people dare to imagine what comes next. Because the most exciting project of all might be one we haven't conceived yet, waiting for some brilliant mind watching this to say, what if we tried it this way? The future isn't just something that happens to us, it's something we build, one staggering idea at a time.